I'd like to introduce. We have Denise from New York. Hi. And we have Denise, and we have John Alexander from Kansas City. We have Paul Stubbs, who's in just south of Jacksonville in Florida. And finally, we have Keen Brown, who's our head of product in Seattle. So anyway, wanted to show you all here right now. I'm coming to you from Phoenix, Arizona today. And so we are spread across the United States. And I've been working with the Project Bonsai team for a couple years, and we've developed some really fun new features. But today is a time to talk about what we've done over the last quarter. And we have 4 major things that we're going to talk through today. But the first one is it's a demo that John has developed. And so, John, I would like you to tell us a bit about the first new feature, which is the deployment of brains through Azure IoT.
Sure. Now, traditionally, we've been able to deploy Project Bonsai brains through Docker and the Azure CLI, but now we can use Azure IoT Central to publish trained Bonsai brains as cloud service modules and run on AI or run on the edge with AI using IoT Edge and the Moby engine. So let's go ahead and jump into this. So here we have the Bonsai UI here. We've already trained a brain. And just to give you a little sense of what's going on here, we're training the brain to balance a ball. And we use the simulator to be able to do that. So we've already trained a brain to move to the center. We want to avoid falling off the plate and then make sure we go into the center of the plate. Now, in order to export the brain, we'll just click here on Export Brain. You can see our name here. And then we also have different architectures that we support. We support x64, AMD or Intel systems on 64-bit or 32-bit hardware. Those general purpose systems for Linux. We also can use ARM64 V8 for 64-bit RISC systems. And then ARM32 V7 for 32-bit RISC systems. So I've already exported a brain, and we can take a look at that. Once it comes up, we can view the deployment instructions here. And traditionally, we would have used Docker pull once we've logged in and authenticated on our repository. And then we can run that. But now we can do it with Azure IoT Deployment. So let's go ahead and do that. And you can see I have all the information that's automatically given to me so that I can go ahead and publish my cloud service module to my device. So let's go ahead and do that. I'm going to copy this here. And now I'm going to go ahead and do a couple of things. First, I'm going to go ahead. I can set up my Azure IoT portal URL inside of my Bonsai portal setup. And I've already done that. So I can click here, and it's going to take me to Azure IoT Central. Now, in order to get my brain on my device, I have to update a device template, which tells the device running on Azure IoT Edge exactly what capabilities it has and the modules to pull down and use. So to do that, we're going to switch to Visual Studio Code. And here is my template that I would use just like with any other IoT device using the Azure IoT Workbench extension inside of Visual Studio Code. And so here's my deployment template. So I can come down here. I've already got one module in here. So I can just put a comma here and then go ahead and just copy this in. I'll paste this in here. And so we can grab our brain called Moab1. Looks like it pulled in a little bit too much, but that's okay. No problem. And we'll get rid of that extra because I already have a module here. I don't need that. So we'll get rid of that extra. There we go. So now I can simply click on my deployment template and build my IoT Edge solution. Once I've done that, I'll switch back over in the browser to my device template, which I have here called Moab. And now I want to go ahead and version this. So I'll do that, give it a new name. It's going to create that new template. And so we need to update that with our updated template that we created for deployment. So we'll do that and replace that with our new file. So we'll click open there. We can scroll down here. We can see both brains are there. And click save. Close this down. We got to remember to publish this because that's always important. Now, if we had other capabilities for, telemetry or commands or something like that, those would show up here. So let's go ahead and publish that. And now that we've done that, we'll just go over to our Moab device. Click here, and we'll migrate this new device to Moab v2. And so now we can see that it's provisioned, and we've got our new module running on there. It'll show up here in a second, but let's switch over now to the terminal. And let's see what's going on here. We're actually on the Moab device itself, and we'll use IoT Edge List to be able to see that. We can see that the Bonsai brain is running. So let's go ahead and reset the bot. And now, switch over. We can see our Moab device running here. Go down here. Click on our brain here. Oops. There we go. And so now it's balancing the ball. And I was able to download that. So I could easily, if I had many different devices running in an industrial floor, I could simply push that brain to as many of them as I needed to. So that's a little bit about Azure IoT. You've seen us be able to deploy that using the new function. We walked through using VS Code through a streamlined workflow, and we're able to easily push that out.
Yeah, John, this is really cool. When we first got this feature working, we had 3 Moab units, and this is our sample app. This is the thing that we use to test end to end, and we got the idea too. You deploy brain to one, and then moments later, the other 2 light up as well. Mm-hmm. And it's really cool. Right now, we're testing swapping out the brain kind of in real time. But we were talking the power of this is not just this one-way push from Azure IoT. It's to be able to read back information from the device. So we're thinking it would be really cool to like hobble one of the motors, kind of break a motor and have it report back up. And then when it reports back up to the cloud, it could trigger a retrain of the brain. And when we come back to the next demo, we have a scenario that we discovered yesterday with literally that scenario. One of the servo motors kind of changed its behavior. Well, it didn't change. I grabbed the wrong servo. And we're like, oh, this would be a great example. So we'll be working this probably into the next quarterly demo. By the way, for those of you that are just joining us now, again, my name is Scott Stanfield. You're watching What's New with Project Bonsai. This is a quarterly show. We're going to be featuring everything that's new with our product, which Project Bonsai is all about building autonomous industrial control systems in a low-code environment. And although we are using these little robots, it's not just for robotic control. We have customers that are using our software for supply chain automation, for industrial automation systems like big industrial augers, or really kind of automated decision making. We like to show these smaller systems because it's something that we can actually have and bring with us on the road or show you on the table. So that's actually probably a good segue. Hey, John, thank you. We have this video now that we want to show you to tee up our next feature, and it's all about visual authoring. And with that, I'd like to just roll the video and we'll come back and talk about it. So stay tuned.
What if you had the power of data science at your fingertips? to add AI to your equipment, systems, and processes without writing code. Microsoft Project Bonsai mirrors how engineers think and solve problems by transforming whiteboarding into AI. For example, travelers around the world hesitate to check bags because they're afraid they'll get lost. Here's how AI can help. Using simple drag-and-drop blocks, engineers create the skills and strategies that the AI must learn, so it understands not only what to do, but why. Engineers can even import existing algorithms for specialized AI functionality, like automatically recognizing baggage size. Then, the supervising AI safely practices millions of possible scenarios in simulation, so it knows what to do even in the most unusual circumstances. So as disruptions occur, the system adapts, and bags are delivered at the right place at the right time. Not only does Project Bonsai focus on adding value for those closest to equipment, systems, and processes, it also helps deliver better experiences that grow customer trust.
So we've got a great demonstration of this whole visual authoring. I'd like to bring on Denise now. And Denise, hey, you know, you and I were watching this video like 2-3 weeks ago when we saw it. It's beautiful. And then in parallel, we're talking about what do we do to kind of tee up this brain design for this little guy. This is a brand new robot that we're using, and it's called the Quasar Cube, and it's really wild. And there's a little bit of math and physics and engineering behind it. And it's important to understand a little bit because it's going to make the demonstration of what I'm going to show you after Denise talks a bit more understandable. So Denise, why don't you tell us a bit about your background and help us understand the cube so we can move on.
Yeah. So my background's actually in mechanical engineering. I have a master's degree specializing in reinforcement learning for robotic control. But I'm definitely not a software developer or an AI expert. My expertise is around the dynamics of systems.
Yeah.
So yeah, I'm going to be talking a bit more about how we break down this robot into the machine teaching problem. That's what we call it for how we design these complex AI agents.
Okay. Sounds great.
Yeah. Let's start by talking about, you know, as you mentioned before, Project Bonsai is typically meant for creating AI agents for really complex systems like optimizing factory logistics or controlling a chemical reactor. Then why are we using this little robot? Well, it's small and compact, so it can fit on my desk safely, and I can explain it in a very short amount of time to a wide audience so that we can break down this whole program or this whole brain and how we're going to design it. So let's start by looking at this system. It's actually, we can break it into two sub-assemblies. The first being this cube here. It consists of a voltage signal going in to control this motor here on top. And it does so very accurately and precisely and smoothly. This assembly here might also look like a motor, but it's not. It's actually an encoder, a very precise encoder that tells us the angle of this rod. When it's fully assembled, the Quasar cube here is an inverted rotary, or it's a rotary inverted pendulum. Now, what is that? Well, it's a pendulum where the objective is to balance the center of mass up above the pivot point. And this system is inherently unstable. And that's why we need active control to maintain this balanced position. And that makes this a great benchmark for testing control strategies. So some examples of inverted pendulums that you might have seen before are cart pull, which is a linear cart that moves back and forth to balance a pull on top. And that was actually one of the first samples built into the Bonsai platform. A real life example would be a Segway or hoverboard where the human body is actually the pendulum. So with that, you know, you might be wondering, okay, why are you demoing a new robot and not cart pull or even Moab, our ball balancing robot? Well, the answer is that this system is different in one very important way. That is that it starts in the equilibrium position with the pendulum hanging down. That means, you know, if I disturb the system, it will naturally return to this equilibrium state. That's different than, say, Moab, where we start with the ball on top. If I disturb it, the ball's going to fall off the plate. It won't naturally return to that starting point. So that is what makes this system slightly more complex and great for demoing the new machine teaching features that have been built into the Bonsai platform. So now let's break this down even further into our states and actions. So first we have our action, which is the voltage coming in to the system, and that's controlling our motor. We then have our states. We have our motor angle, which we call theta, as well as its velocity, theta dot. And then we have the angle of the pendulum. We call this alpha, and its velocity, alpha dot. Now, those 4 states can completely describe this system. But let's look even closer at the constraints that we should put on those states and actions. The voltage going in is constrained to plus or minus 3 volts. The motor angle we constrain to plus or minus 90 degrees to avoid interfering with this encoder cable. Now, the pendulum angle is where it gets interesting, because when we're balancing up here in the top, this is an unstable equilibrium point, and it's really our goal where we want to go. Now, we can exploit a mathematical trick and some traditional control engineering to program a controller that's going to work really well to balance up here in this range. The controller we're going to use is called a linear quadratic regulator. And Scott will show you how in just a few lines of code, we can very efficiently balance here. But what about when our pendulum is anywhere else? Well, we need to teach our system to swing the pendulum up into this balance region. So with that, I've sort of broken down the states and actions of the system. Let's move over to my whiteboard, and I'm going to actually design the brain out for you. All right. So we start, as I mentioned before, with our inputs. And those are alpha, alpha dot, theta, and theta dot. We're then going to have our balance concept. And as I mentioned before, we're going to program this concept as an LQR controller. We're then going to have a second concept for swing up. And I'm drawing this concept in red to represent that it's going to be a learned concept. We're going to use reinforcement learning to learn how to swing up. Now, there's a third concept that I didn't mention before, and that's going to be our selector concept. Now, this selector concept is going to choose which of these other concepts, swing up or balance, the brain should choose. So we have the inputs coming in, and based on the state of our system, our selector will choose, is it going to balance or is it going to swing up? And what's really cool about this selector concept is we don't have to program in when to choose which concept. It can learn those fuzzy boundaries.
Yeah, Denise, this is the part that this is why we chose this demo.
Exactly.
To really illustrate these two concepts, or being able to switch between this new concept of the programmed function of the linear quadratic regulator versus the learn system. And it's like, I have to say it, I know we realize later it's not, but that little child's toy with the ball and the cup and you like swing it. And I saw one in the Grand Canyon gift shop yesterday, and I almost bought it just to bring it. But the idea is that you have a strategy to begin with where you're swinging something in this case, and then you switch to a strategy of trying to catch it. Now, the difference in that toy is that the ball stops and lands and nothing happens. In this case, we have to continuously balance it, which makes it really difficult. But the idea of knowing when to go back and forth is key. So I'm sorry, I just keep going. This is great.
Some great points there, Scott. So I think it's good to point out that what we have here, what I just put in this blue circle, I wanted to highlight that that's going to be our brain, and it's sort of made up of this concept network. We've taken this this complex thing that we want our system to learn, and we've sort of broken it down. into the balance concept, the swing up concept, and the selector concept. And this also adds transparency to our AI agent. So let's see, what else did I mention? Oh yeah, once we've selected a concept, we then get our output from our brain, which is our control action, the motor voltage.
Yeah, we have that between -3 and 3 volts, because we found if we put a little bit more, the motor swings too hard and spins around and can even knock itself off. So we have some boundary conditions in the simulator already, just to kind of match the real hardware constraints. So
yeah, so with that, Scott, I'll hand it over to you to actually build this brain on the Bonsai platform.
Okay, I'm going to keep you with me. We're going to go a little bit off script. I'm going to keep you with me as I go through this, because
all right.
This is a good time to kind of match what you've been showing to the implementation. And so going from the theoretical brain design to the actual coding. So we'll kind of do this together. And tell you what, so I have loaded on my screen here the Project Bonsai workspace. Oh, by the way, I want to mention there was a great question from I got to look at my notes. A question from AMN Lima, who asked, "Is the Moab platform for sale?" And the answer, it's not for sale right now. Right now we have our first limited run of Moab units are reserved for our partners and customers. However, we do have all of the plans, the software and the hardware and the 3D CAD diagrams available online at a link. Tell you what, share my screen. Let me go show you my screen. You can find everything at aka.ms/Moab is the landing page for the whole system. And then a little bit farther down is Moabian. This is all the source code and the brain details. It's not, one of the reasons why we want to, well, it's difficult to keep making these, but we have a lot of interest in selling them. One of the reasons why we keep it on hold for now is as we develop, look, when we get back in person, the idea was to have this for a trade show. So we would all be meeting in person. We'd have a lab, you can come work with it. For now, you do have a simulator. So the full simulator is available when you go to Project Bonsai. In fact, when you go to create a new brain, you can choose the Moab sample. Now, this is just simulated. It's not the physical thing. In this case, we have the two simulators loaded. Denise, I have the Moab and the Cube. So I'm going to switch away from now Moab and go back to the Cube simulator. This sim is part of our Python sample set. Denise, this interface.json file?
Yep.
Right here.
So this is basically what defines the interface between the simulator. So that's the virtual representation of this system that we're going to be training on. So it's the interface between communicating with the simulator and the brain.
Mm-hmm. And there are the numbers you mentioned, the theta, the alpha, theta dot. Now, these are some of the initial values. And there's more in here because as part of the modeling of the system, right, we had a lot of constants necessary for this. So this simulator was built before we were even at this point with Project Bonsai. And we took it and added the interface.json, and using the Bonsai SDK, we're able to bring the two together and then wrap it in a Docker container, push it up to into our workspace, into the Azure Container Registry. So while we have the ability to pull in other simulators, Denise, your favorite, Simulink, we can bring in simulators from other spaces. In this case, this is what we did. We imported our own simulator using the SDK details. So
Quanser does have a Simulink simulator for the Quanser Cube.
Yes.
That was one thing. Can we throw up the link for the Quanser Cube? In case you're interested, you can buy the Quanser Cube. These are sold as educational tools.
Yes. Quanser Cube. And this comes with the Simulink package in the toolkit. But we built the Python simulator standalone independently, so we could wrap it and put it up to do this. So we've already added the simulator. I launched it, and that same the interface is now exposed through this JSON. I'm sorry, the Inkling that we need to go forward. So this is the state of the simulator at any given point. The theta, which is the primary angle, that's what we control, and is between negative. Here, let me show you. Between these two angles, we don't want to go all the way around because we found if we go too hard, we can knock the arm off itself. And then we have the theta, the alpha, which is this rotation. Our goal is to get this thing upright. and then finally acceleration for both of those. And there's we only control the voltage left and right. It'd be really cool to hook up on the back like a potentiometer where I can dial in the different voltage to see it move. But for now, we'll go with this. So from the simulator, I'm going to create a brain, and this is key. So let me do Scott QQ. We're going to create a new brain. Now, what that did here in the Bonsai interface, if you've been using Bonsai for a while, this is new because this is part of the whole new visual interface. Behind the scenes, there's an Inkling file, which is the definition of the kind of the interface between our simulation and the goals that we want to achieve. This visual authoring interface on top of it is going to allow us to do a couple things. One is this initial creation of our concept. So by clicking on concept here, you can see that there is a loop, and Denise talked about this before, where we take our input state. Let me zoom in. Let's see if that's visible. So we take our, Denise, can you read that?
Yep.
Yeah. So these are the 4 variables, and we want to teach it to do something. Well, think about what Denise decided earlier. Our first goal is just to get it to get close. We want to move that motor back and forth until we're close to swinging up. So let's type that in. So we'll change our name to swing up. I have 3 global constants I need to set up that I'll be using throughout the rest of this. And the first one is the theta. Let's see, the theta. Put it down. I have notes here. So it's theta rotation threshold. And so I don't know. We talked back and forth like how do we remember between theta? I just remember because in trigonometry, theta was that angle, like the primary thing. In this case, that's the angle I can control with the voltage. And we're doing a threshold of positive and negative 90 degrees, so it doesn't swing too much. And then the corresponding constant for alpha, we have the alpha balance threshold, which is 12 degrees. I don't know how we hit on 12. Do you remember, Denise?
I think it was probably some
arbitrary
experimenting. But yeah, 12 degrees represents the region at the top that we're trying to stay out.
So once you kind of get it close between these 2 states here, then we're going to use a different control strategy. Okay. So I have one more to type in. This is the simulator visualizer. And I provide a path to it. And cube viz. Okay. So we have our 3 constants set up for our brain. We're gonna let me show this type definition. We were talking about this earlier. This is interesting. So again, this is the data coming back from when we load the simulator. This is our interface into it, and look at these numbers. I mean, first of all, it's a lot of significant figures, and if you don't remember, and this looks awfully close to pi. It turns out we don't need this specificity. And if I create a new structure called observable state, let me back this up. Observable state. I can kind of remap these and get rid of the ranges. And this is one of the great things about our reinforcement learning engine is that even by removing these constraints, it, first of all, decouples me. This is wild. This was something that took me a while. Like, wait a minute, if we remove constraints, we might have a more generalized brain and it will learn faster. This is where some of the RL kind of goes beyond me. But I can take that and save it. And then downstream, we can let the system explore more of the physics. Really, what was happening is that we had some acceleration constants that were too low. And because the reality of this machine allowed it to go faster, by breaking this up, we can remove some of the constraints on the system and get a more generalized solution. So instead of where do I go? It's here.
Right up there. So that's the input node. And yeah, we'll change that to observable states. Okay. So that
so now there's a mapping. In this case, we've removed constraints, which is pretty wild, but it's been working great. So now let's move forward back into this concept. Now this learned concept is the key point that we've had since Project Bonsai's launched. We're going to come to these other ones shortly, but let's continue setting up this the learned one. So we're at goals. Okay. So what are our goals? If you recall, Denise, you remember the goals that you taught me for this? We want to, let me go and add 2 goals. And the first one is we want to, well, first, let's avoid hitting the motor limit. So I want to avoid, I'm going to copy this syntax here and paste it in. So we're going to avoid, I think I put it in quotes. So hit motor limit. We're going to give it like a hard constraint where the theta, it was in this case, it doesn't matter if it's positive or negative, so I'm going to wrap an absolute value. So we're going to make sure that the theta stays within the target region you know what, I have this code copied because we're using a mix of radians and degrees. Okay, there's our first goal. And our second goal, I'll copy, is our primary goal. We want to reach this swing up state. Up.
Yeah, and you can also see we've highlighted our first error, and I know what it is, but it's great to see that we have those indicators right in there.
So it's the state, right? Because it's not flowing through. Is the state?
That's one right there, observable state. But also the function degrees to radians. We need to
I haven't typed that in. Yes,
add that as well.
Okay.
So you can see those two constants we added, theta rotation threshold and alpha balance threshold.
Yeah.
Those are used in our goal definition here.
All right, let me go back. Yes, I should have done the function first. That's cool. Man, you're better than the little red squiggly lines. Okay, so it's funny. I'd mentioned that we're mixing degrees and radians. Well, because we're doing that, we need a function to help us with that. So this is going to convert the human degrees into radians, which is what's necessary for this. So this is a little bit of function that we're going to use as part of our goal definition. So if I go back and add the goal, and I'm just going to copy this from the clipboard. You don't have to watch me type that. And this is observable state. Now, this is a lot of kind of gluing together, but keep in mind that the fact that I can express this in kind of human terms we have two goals. It's to don't knock the motor off and then get this thing close to within 12 degrees plus or minus. We have some absolute values in there, and we have degrees and radians. In fact, we thought about changing the whole system to just degrees or just radians, but I said, we'll leave it. We'll leave it because it's truly how we solved this problem with the original simulation. So we have I think we have one more thing to do. Yeah, we have a lesson. So we have to give it a lesson plan. So while we have these overall goals, we want to initially constrain the whole system into something that's more learnable. Just like you would teach maybe a child how to play piano, which, God, why did I go there? Yeah, I took piano lessons
But
forever.
so the thing is, I'll jump in here because we're using a learned concept, as I mentioned. So we're going to be using reinforcement learning for our agent to learn how to swing up. We defined our goals, but now we're defining the lesson. So every time it's practicing, what are those initial conditions?
And
so
they're smaller.
Yeah.
And the initial conditions here are smaller than normal. Mm-hmm.
Yep. So we define the initial conditions. So, what we're varying, but also what's staying the same. So we're not varying the parameters of the system, like the mass or the length of the pendulum. But we could vary those if we wanted. But for now, this is the lesson that we've chosen.
And one of the things that we learned this morning is that the resistance of the encoder is different from the ones that we've been using because I have my box. I grabbed this rotation, this motor, and it came straight from straight out of a box. And I thought it was the same, but it was actually different. And there's a small amount of internal resistance that we had modeled before, which is a great reason to model this in the future, where we could expand those parameters into two different types. So we'll save our initial lesson here. And anything else?
There are some training parameters which we could change. I think we can leave them as they are for now, but these are all configurable.
Yeah, and the reason why we were changing that one training parameter is that we want to give the system, we know from experience it takes longer to swing back and forth and balance. So that lets it go longer before we declare a failure and start over. So, okay, what you've seen so far is in the visual editor here, we have this whole loop. I think it's time to introduce the next concept.
Yeah, and I think it's a good time to also introduce one of the new features, which is the different concept types. So if you've used Bonsai before, this swing up learn concept isn't new. That's the concept type that we've always had. What's new is that we now have in the concept menu bar there, we have the learn concept, selector concept, programmed concepts, and imported concepts.
Yeah. And we've spent so much time here. And the reason why we're now going to drop into this programmed concept is because this is where really how we've solved this problem before. You had mentioned, Denise, earlier that there's kind of a known solution when alpha gets vertical. And it's nice because the way the math works, some of the math cancels out. And it allows you to have the simplified implementation of it. So I'm going to drop this. Let me go back to our function definition.
Yeah.
And,
so now with the balance concept that Scott's building, which is the program concept, he's going to add in the function, the LQR controller. So here you can see it's just a few line of code. The thing is, you do sort of need a degree in engineering, specifically control engineering, to know how to design an LQR controller. It's not trivial. But if you have that specialized knowledge, it's only a few lines of code, and it works really well. And these are controllers that are used all the time in existing industrial systems, and engineers have a lot of trust in them.
Yeah, and these results were achieved empirically. So from the simulator, we solved it near this space, and that's why this vector of 4 numbers, we're able to come up with it. You could also pull these out of if your simulator in Simulink. So we're able to solve this piece. But it's funny. We'll see that these values were derived from a different sensor, a rotational sensor that had very little friction. This one adds a bit of friction. So we have an interesting bit of behavior that we hadn't seen before, but it's kind of fun. Okay, so we now have this just basic function, right? So you stick in 4 numbers, which is our observable state, and it returns the motor voltage. So now the question is, for this function, this program concept, what do we call this instead of swing up? This is just balance, right?
Yep.
Yeah, this is what we do when we get to the top. So we have some gluing up, right? This is just a standalone function right here, the linear quadratic. Oops. Yeah, let me leave that for a second. Oh yeah, that's fine.
Yeah, so that's fine.
Yeah. Okay, so let's wire this up. This is my favorite part of the demo, is dragging the little lines around. So now we have these two concepts. So remember the classic one and the new one that we're releasing now. And then we want to somehow magically select between them, right?
Yeah, so one thing, just make sure you define the output type for that program.
Instead of a number, it's the sim action, which is
exactly.
Now, can I just train this right now, or do I need to build balance?
I'd wait until we build up the whole brain. Okay.
So let's drop in now the selector, which is going to allow us to choose between these two that we want to activate at any time. Let me get everything on the screen. So first, I know that this concept, this is the it's going to switch between the control strategies, or switch between the two concepts. And I'm going to wire these two together. So it's going to be using swing up and balance. And I know that, again, its output is not a number, but it's the sim action. And let's see.
You got to wire up
the global state. And, you know, this is where I would just love to spend time to go, like, get all these lines arranged. But in the interest of time, I'm going to hit the arrange button. Okay, so what do we got here? We have another red arrow. I need to drag this out, and just like we had a lesson plan before, just for the swing up, I need this kind of overall macro lesson plan, which again, these are some of these constants, and then we'll put the goals in, and then I think we'll be ready. Lessons. So this lesson is, I think we just picked the same constants here. We could have something more elaborate with multiple lesson plans, but in this case, that was achievable. And then finally, we have goals. So we have a new goal here. Let me drop it in. Okay. So we still have avoiding the motor limit. And we want to now drive the pendulum angle so it's less than, so it's within that threshold range of 12 degrees. And I think we have all the components in place. Denise, am I missing the observable state here?
Yep, there you go.
State, save that. And cool.
Yeah, now, and one thing, I did notice there was a question. that came in a bit earlier about, how to avoid reaching local optimas when we're designing this type of system. And I think what we just saw there in the goals for the switch control strategy, these are the high level goals for the system. So when we try to set those high level goals, it allows us to avoid those local optima. And ideally, it definitely takes some experimentation to really define those goals properly.
And we'll see that in some of the it'll try to bounce out of some of the local optimas, and we'll see that in in some of the training graphs right now. Let's see. I'm not going to train the entire thing, but I can just go ahead and kick it off. I'm building the balance component to it right now because this is a static function. This is trivial. And then we'll go back and build the swing up. I want you to watch here. You can see it's a little bit hard to see probably. Let me zoom in. I'm trying to get that little circle right here is spinning around green. And now it's green. We're good to go there. So now I can go back, and that component has been taught. Now I can do the same thing with swing up. I can go start the training here. Now this will take longer. I think in this case, we're going to do, Denise, I'm just going to jump straight to the brain that we had trained earlier, because now this entire system is starting to go. And while this is spinning up, let me go down to the final one. So this is, let's see, did I start this earlier? Yeah, at the beginning of the broadcast, I started this brain training, and it's clearly already it has hit its goals earlier today. But let's see, let me train it. I'll start this up again. Okay. Here we go. So what's happening in the background, it's spinning up the containers that's necessary to really learn the system. And you soon will see as the system spins up, it starts the simulators, we'll see down the bottom here some interaction here. We're going to drop a link at the end where every Thursday morning Denise and John will do a live webinar where we walk through training a system from start to finish. It's not 3 hours. We've been running for 3 hours because we keep starting and stopping it for the demo. And you can see as it tries to approach the overall goal satisfaction of balancing, avoiding hitting the motor limit and reaching the swing up state. But now as it's going up, I'm going to just toggle back. Just to kind of refresh people's memory what it looks like. We showed this earlier here. And as I kick this off, watch the behavior now. So there's the swing up and there's balance. And when it's actually running, let me stop it again, watch it again. So if I were to try to do this by hand by swinging this back and forth, we're in that swing up goal. I can't do it as a human. There's just too much that's going on. But let me run this again. And there it is. So it's a really great behavior. At the top now, this is where it's running the LQR. On Denise's cube, John's cube, Kirill's cube, and my other arm, this thing stays really straight. And the only difference is that the internal resistance of this arm, is a little too great. And it's because I took a photo of it, it's a new armature design. But man, next time what we would do is just model this and train a more generalized brain. So we'll be back to that. Okay, so Denise, I want to thank you for this. This was awesome. It's very much in depth. I think it was necessary to go this deep to really highlight some of these new features. So again, thank you.
Yeah,
and now I want to. That was great. Thanks, Denise. Bye. And Paul has been patiently standing in Jacksonville, and I hope it hasn't been raining, Paul. I would love some of that weather out here. But Paul, you had a chance to talk to one of our customers earlier. Why don't we? I'm going to ask you to stand there for one more minute, and we'll just let's show them who this is. This is Belle Flight, and we have a short video.
Why don't we start by telling us a little bit about you and what the work is you do?
Sure. So I'm the manager of applied intelligence at Belle, working in the innovation group, and I focus on evaluating and using AI to enable autonomous flight within our innovation products. So that's looking at how AI can augment and enhance traditional pilot operations, as well as fully enable autonomous flight. And how do we do that safely, securely, and at scale? And that's where Bonsai has become part of our strategy for enabling our aerospace engineers and other domain experts to achieve these autonomous systems.
Well, that's interesting. Tell me a little bit more about what the future of flight looks like.
So the future of flight will always have humans in the loop, and really, at least our vision of it is leveraging autonomous systems to safely operate more aircraft at scale, while ensuring and enabling human interaction where necessary.
And how does Project Bonsai help fulfill that vision?
So specifically, Bonsai and really its low code approach and machine teaching capabilities allow our domain experts, such as aerospace engineers like myself, to prototype, train, and deploy autonomous systems without being AI specialists.
Well, that's interesting. So if you didn't have the Bonsai platform to use this low-code approach, how would you go about building these types of systems?
Well, I guess the short answer it would be significantly more challenging, and we need a much larger team. And I don't think we would be able to fully realize the potential of AI and autonomous systems.
And so what kind of solutions have you been able to build with the Bonsai platform using this approach?
So one of the ones we've been able to do is we actually worked and collaborated with Microsoft to develop a vision precision landing system for a small autonomous drone, and that is, we were able to teach a drone using monocular vision as its sole perception source to locate and safely land on a given vertiport. And so that's part of our expanding research into integrating this AI into our systems.
Can you tell me what's next for Belle, Bonsai, and Microsoft?
So next steps for us and the team are starting to look at what we call detect and avoid, or the challenge of making decisions while the aircraft is flying and encounters a obstacle where it has to make complex decisions around competing objectives.
Thank you for taking the time to talk with me today.
Let's bring Paul back in Florida, put him on screen. Hey, Paul, sorry, I flipped the order of the videos. You might want to tell us who that was.
Yeah, so that was Grant Bristow from Belle, and what's really interesting, we've been working with Grant and Matt Halvey from Belle as well on a whole number of systems around urban air mobility using Project Bonsai and Project AirSim. We've put together a short video that kind of highlights some of the work that we've been doing together, and maybe we can run that now.
Our vision at Belle is to solve some of the world's biggest challenges using unmanned aircraft. Imagine being able to monitor entire forests for fires around the clock, search every nook and cranny of a mountain for a lost hiker, or deliver life-saving medicine anywhere. Autonomous drones will allow us to operate at a scale that we can't operate at today. We'll be able to reach more customers, we'll be able to make a more global impact with the limited resources we have. We start by using AI to teach drones everything we know about flight. How to take off, land, navigate, adjust to the weather, and because they need to do it safely without causing any damage or injury in the real world, we're using Microsoft Autonomous Systems to practice in a simulated environment. Simulation is the great enabler of AI because it gives us a hyper-realistic environment that allows you to train AI as if you were doing the operations for real in the real world. It allows us to compile hundreds of thousands of hours of AI training rapidly and to deploy AI at a scale that wouldn't be possible without it. And when they fail, they learn but without causing disruption or downtime. Once deployed, autonomous drones can operate continuously, safely, and reliably while keeping humans in control of every flight. Success for Belle is accomplishing missions that are going to change the world. And that's why we're building with Microsoft.
Man, that looks a lot more fun than when I first flew my drone directly into a palm tree, and literally the first flight. And of course, it's on video, so I didn't ruin it. But that's really good. And Paul, as long as I've known you, you've really been really interested in the drone space, and so I think it was really nice that you and Grant had a chance to talk.
Yeah, and there's a lot of work going on here in Florida. One of the reasons I moved out here, there's a lot of work happening on drone space here with NASA, and the work that Belle's doing. The simulation space is super hot over on the East Coast here. So a lot of exciting stuff happening.
Yeah. Well, look, we have a chance now to also bring on, I thought it'd be good for you and I to talk to Keen. Keen Brown is our head of product for Project Bonsai. And you and I can ask him about, hey, Keen, did we cover your features right? Did we get
Yeah, it was great. It was great. I loved watching it.
Yeah, it's the three of us have been talking about this for a while, and we've had on a small scale lots of fun kind of toy and demo samples. By the way, this thing is still going. I just want you to see that. We've had fun building these, but to see and hear from our customers, and I want to highlight them every quarter, but to see what they're doing really allows us to stretch beyond kind of this kind of deep developer view and engineer's view, but out to something broader. Now, Keen, what can you tell us over what you shipped over the past 6 months? What piece are you really excited about?
Well, clearly the pieces we're talking about today are sort of the culmination of not just a few months, but several years' effort. Horizontal platforms themselves are super exciting because of this broad set of use cases. And, with things like the low-code visual authoring and finally getting sort of the goals and concepts to a certain place, we're, really finally starting to make that impact in terms of enabling all these different kinds of scenarios to be developed. It's always a challenge building this kind of technology because we have to keep an eye on both power and usability, and we're trying to thread that needle here with these latest features.
I think that's super interesting, and the parts that are interesting for me is the having multiple concepts and to be able to break things down, because it's hard to keep track of these complex systems, but I can solve smaller problems.
Yes, concepts themselves, they come from that, both the idea that comes from engineering in terms of decomposition and computer science, right? Decomposition. There was also biological inspiration in terms of, if you think of a brain of a human or any creature, there's a set of different portions of the brain that have different functions, and we're kind of allowing users or enabling users to recreate those pieces. And it's we believe a critical piece, not just for simplifying, enabling more power, but you'll also see features out that help us enable kind of traceability or explainability with that, where now that the subject matter expert has decomposed their AI problem into a set of components, we have a way to provide a trace and a relationship between those components. And we're excited about all of this and hope that customers like it.
Yeah, you mentioned the decomposition. And one of the reasons why we had Denise go through the machine teaching thinking and the ideas, there's like this architecture or the way of decomposing this problem, and then you go into the design of the brain. And I don't know about you guys, my background is software engineering and programming, and this has been a really good experience for me to kind of look at these problems through the lens of an engineer and learning more about the world of simulation, not only of our own custom sims that we use for the demos, but really using and looking at our customers' sims. And they work at wildly varying control frequencies. The problem space is really wide. Keen, I'd mentioned earlier I don't think I mentioned by name, but the use case for Frito-Lay, for Pepsi, and using an auger to manipulate the cornmeal and the steam to make better Cheetos. And we love telling that story. Usually it's accompanied with a bag of chips, but do you have any other kind of recent customer highlights that in different areas that you could touch on?
Yeah, I'm really excited about a lot of the work we're doing in areas like factory logistics. We've been working a lot with our partner AnyLogic, who builds a simulation specifically for modeling those kinds of problems, and as well as several partners that have helped with consulting in that area and customers working on those systems. We of course continue to do work in all sorts of chemical process kind of industries, from things like polymer mixing to managing CO2, work on energy, things like you can imagine with energy trading and alternative energy, using a battery and thinking about when to store energy in that battery. All these scenarios have been great.
Those, like some of the chemical engineering scenarios, the state space is huge. This is only 4 states, really just 2, and the other's the velocity. But some of those can be a much larger state space. And why don't you tell us about some of the the accelerators? I missed that one.
Yeah, we have a set of solution accelerators that we're releasing and a set of samples. They include things for like operating an extruder, like the example you gave before. We have ones around controlling other chemical processes, one around factory logistics. You'll see some of those popping up into the UI in the not too distant future.
Yeah, certainly something that's on everyone's mind is just the world supply chain and how fragile that is. I can't imagine. Well, now I can. If you have a simulation for it, you can now plan out all these scenarios better to maybe streamline your orders.
Yeah, that's one of the powers of simulation itself, actually, and it allows you to model things that are rare events. Mm-hmm. And going forward with the way we think about how you can configure and use simulation as part of teaching the AI, we think a lot about how can you configure the sim to cover and sweep the various events that you might expect, that you expect the system to be able to handle. And certainly recent issues with things like supply chain and logistics planning have taught a lot of people about putting some of those black swan scenarios in and modeling those out, and building systems that optimize and can account for that.
Right.
Well, and I was thinking, one of the things that I liked, as these get more complex, I'm a visual learner, and so I really love the progress that's been made on how easy it is to quote, draw your brains, if you will, with the design surface. And I think that's just amazing work and really helps me, think about this at a higher level when I can see it on paper like that.
Yeah, like what Denise showed earlier. Showed that on paper. Hey, Keen, thank you. And Paul, thank you too.
Thank you.
Stick around. Stay on. Let's bring Denise and John back. I want to say goodbye to everyone. There you are. And there you are. Great. Hey, thank you all for tuning in. This is our first quarterly show for about what's new with Project Bonsai. My name is Scott Stanfield, and our guests here. Thank you all for joining us. And we'll drop a link in where you can join us every Thursday morning with a live show, one-on-one or one-on-few, and we'll take you through some of the new features. But again, thank you for joining us, and we'll see you next time. Bye.
Thank you.